Right now, somewhere above you, there is a commercial aircraft traveling at approximately 900 kilometers per hour. It is carrying hundreds of passengers. It is powered by engines generating tens of thousands of pounds of thrust. It is one of the most powerful machines ever built by human hands, and it is going almost exactly the same speed it would have gone in 1960. Think about that for a second. In 60 years, computers went from filling entire rooms to fitting in your pocket. Cars became electric. Rockets reached Mars. Medicine defeated diseases that killed millions. And commercial aviation, same speed, same altitude. Almost identical performance envelope to aircraft that flew before most passengers alive today were born. Why hasn't the plane gotten faster? The answer is not money. It is not lack of ambition. It is not a failure of engineering. It is physics, specifically one of the most violent and counterintuitive physical phenomena in all of aerodynamics. A phenomenon that destroyed aircraft, killed test pilots, and took decades of science to fully understand. And once you understand it, you will never think about your cruising speed announcement the same way again. Stay until the end, because the last point reveals why going faster would not just be dangerous, it would make the physics of flight itself work against you. Most people have heard of the sound barrier. Most people associate it with fighter jets and sonic booms. Most people assume it is something commercial aviation simply never approaches. Both assumptions are wrong. The speed of sound at cruising altitude, approximately 35,000 feet where temperatures drop to minus 56 degrees Celsius, is approximately 1,060 kilometers per hour. Commercial aircraft cruise at between 850 and 950 kilometers per hour. That is between 80 and 90% of the speed of sound. Commercial aircraft are not far from the sound barrier. They are deliberately flying just below it. Every flight, every day. And the reason they stop there, the reason engineers designed every commercial aircraft to cruise at exactly this range and no faster, has nothing to do with the sound barrier itself. It has to do with what happens to air when an object approaches it at those speeds. At low speeds, air moves smoothly around a wing. It parts ahead of the wing, flows over and under, and rejoins behind it. This smooth flow, called laminar flow, is what generates lift. It is what keeps the aircraft in the air. But as speed increases, something begins to change. The air ahead of the wing has less and less time to move out of the way. The pressure waves that normally travel ahead of the aircraft, warning the air, so to speak, that something is coming, begin to compress, to pile up. And at a certain speed, well below the actual speed of sound, those pressure waves compress into something the engineers call a shock wave, and a shock wave changes everything. Here is what a shock wave actually does when it forms on a commercial aircraft wing. The moment a shock wave appears, the smooth laminar airflow over the wing behind it separates. It becomes turbulent, chaotic, and turbulent airflow over a wing does not generate lift the way smooth airflow does. Lift drops, drag increases dramatically, sometimes by 200 to 300% in the most severe cases. The aircraft suddenly needs vastly more thrust to maintain its speed. The engines, already running at near maximum efficiency, cannot compensate. The aircraft slows, the shockwave moves, lift returns, the aircraft accelerates again, the shockwave forms again. Engineers call this cycle Mach buffet. And in its most severe form, it creates violent, uncontrollable oscillations that can exceed the structural limits of the aircraft. In the early history of high-speed aviation, before engineers fully understood this phenomenon, it killed people. Aircraft in steep dives approaching high speeds in the 1940s experienced sudden violent loss of control as shockwaves formed on their wings and control surfaces simultaneously. Pilots who survived described the experience as the aircraft suddenly having a mind of its own. Control input stopped working. The aircraft did what the shockwaves dictated, not what the pilot commanded. This was called compressibility, and it was one of the most dangerous and least understood phenomena in early aviation. The sound barrier was not a wall. It was a zone of aerodynamic chaos that began well before the actual speed of sound. As aircraft designers began to understand compressibility in the late 1940s and 1950s, they identified a specific threshold for every aircraft design. The critical Mach number is the speed at which airflow over the fastest moving part of the wing, usually the upper surface near the leading edge, first reaches the local speed of sound, even though the aircraft itself is still flying below the speed of sound. This happens because air accelerates as it flows over the curved upper surface of a wing. the air over the wing moves faster than the aircraft itself, which means it reaches the speed of sound before the aircraft does. On a modern commercial aircraft, the critical Mach number is typically around Mach 0.72 to 0.78. That is 72 to 78% of the speed of sound. Below that number, smooth airflow, predictable lift, efficient flight. Above it, shockwaves begin forming, drag rises, buffeting begins. Modern commercial aircraft are designed to cruise at between Mach 0.82 and Mach 0.87, slightly above the critical Mach number, but within a carefully engineered zone where the shockwaves that form are controlled, predictable, and managed by wing design rather than catastrophic. Every millimetre of the swept wing geometry, every curve of the wing's cross-section, every angle of the engine nacelle is designed to push the critical Mach number as high as possible and manage the shockwaves that form above it as efficiently as possible. The cruising speed of a commercial aircraft is not a conservative choice. It is the precise upper edge of the envelope that aerodynamics allows. If this is changing how you see that cruise speed announcement, hit the like button and subscribe. We explain aviation science every week. Look at a commercial aircraft from above. The wings do not extend straight out from the fuselage at 90 degrees. They sweep backward. The tips trail behind the root. On a Boeing 737, the sweep angle is approximately 25 degrees. On a Boeing 747, approximately 37 degrees. This is not aesthetic. It is not about fitting into gates. It is a direct engineering response to the shockwave problem. A swept wing effectively increases the critical Mach number of the aircraft. Here is why. What matters for shockwave formation is not the speed of the aircraft, but the speed of airflow across the wing's cross-section. By sweeping the wing backward, engineers rotate the wing's cross-section relative to the oncoming airflow. The component of airflow that the wing's aerodynamic profile actually experiences is reduced by the cosine of the sweep angle. On a wing swept at 35 degrees, the effective airspeed experienced by the wing's cross-section is approximately 82% of the aircraft's actual speed. This allows the aircraft to fly significantly faster before the critical Mach number is reached. It pushes the entire compressibility problem to higher speeds. It is why the jet aircraft of the 1950s, which introduced swept wings, could fly faster and more efficiently than the straight-wing propeller aircraft they replaced. The swept wing is one of the most important single innovations in commercial aviation history, and almost no passenger ever thinks to ask why it exists. The question is reasonable. We understand the physics now. We have computers that can model shockwave behavior to extraordinary precision. We have materials that can withstand far greater structural loads than aluminum. Why is the commercial aircraft of 2025 flying at essentially the same speed as the aircraft of 1965? Two answers, one physical, one economic. The physical answer, drag. Above approximately Mach 0.90, wave drag begins to increase exponentially. Wave drag is the additional drag created by the energy dissipated in shockwaves. Unlike ordinary aerodynamic drag, which increases with the square of speed, wave drag above the critical Mach number increases far more aggressively. To push a commercial aircraft from Mach 0.85 to Mach 0.95 would require engines producing dramatically more thrust and consuming dramatically more fuel for a relatively modest gain in speed. The Concorde solved this by going supersonic, above Mach 2, where the wave drag relationship changes again, but it burned approximately 4 times more fuel per passenger than a conventional subsonic aircraft. The economics were fatal. It flew for 27 years and never made money. The economic answer, time saving. A transatlantic flight from London to New York takes approximately 7 hours at Mach 0.85. Flying the same route at Mach 0.95 would save approximately 40 minutes. 40 minutes at 4 times the fuel cost. For most passengers and most airlines, that calculation does not work, and until fuel costs change dramatically or a completely new propulsion technology emerges, the physics and the economics point to the same conclusion. 950 kilometers per hour, the precise intersection of what is possible, what is efficient, and what the shockwaves allow. The next time you're sitting in your seat and the captain announces cruising altitude and speed, 900 kilometers per hour, 35,000 feet. Consider what you are actually hearing. You're hearing the number that represents 6 decades of aerodynamic refinement, The precise speed at which swept wings, engine placement, wing camber, and fuselage shaping combine to hold the shockwaves at bay. The speed just below where wave drag begins its exponential climb. The speed that the Concorde's engineers proved at enormous cost cannot simply be exceeded without fundamental consequences. The aircraft is not going slowly. It is going exactly as fast as the physics permits, efficiently, sustainably, safely, with hundreds of people inside. The engineers who designed the aircraft you're sitting in did not choose 900 kilometers per hour because they ran out of ideas. They chose it because they understood precisely and completely everything that happens at 901 and decided that was enough.